We've only just begun our treatment of systematic mineralogy, and we're still in, just to kind of remind you where we are in our notes, we're still in native elements, only just beginning. But where we've finished gold, we now must go to other native elements. And so number 2, or big B, is going to be silver. The chemical formula is Ag. In the textbook, it is pages 343 to 344. Before we go any further, get a picture in so you can be thinking about silver or looking at silver while we go through these notes. Last time I think about chemistry as number 1, I think it's better to start with mineralogy, but recognize that chemistry and mineralogy are really interrelated and can't be separated. The mineralogy of silver is that it is a 2.5 to 3 on the hardness scale, and in terms of its specific gravity, it's less dense than gold. It is around 10.3. Now, when we do make these alloys between silver and gold, one of them that's called electrum. It's also why you can have 18 karat gold, because you mix in some density 10.3 silver with density 19 gold, and you'll get some mixture that you can measure very easily on a balance, and then you can know the purity of your gold or the purity of your solid solution. The mineralogy is similar to all these other metals in that we have a 12-fold coordination, and we have metallic bonding. And you get all the different properties that metallic bonding makes, like softness, malleability, conductivity. Okay? When it crystallizes, it should crystallize in the isometric form, but it doesn't. Instead, it tends to crystallize as irregular masses, and sometimes it even kind of starts to look wiry, like this picture right here. Irregular masses to wiry would be what we'd say is our crystal habit that we should expect for silver. Mineralogy / chemistry also has some important things to note here, and the first would be, let's say that we do make these alloys with solid solutions. As an example, there is the alloy between gold and silver, which is called electrum. But there's another one called amalgam. It's very important for mining, and it is where you take mercury and mix it with silver. And this creates this very tightly bonded type thing to pull silver out of its other ore rocks to extract the silver. Now, that might have not been the best description, but that's what amalgam has been used for. Another aspect of its chemistry, you can start to see it here, is that where we should get a nice silver color, rarely do we get, like here's a really nice silver color, right? But rarely do we see silver so nicely. Even your grandmother's silverware doesn't stay silver. Instead, it may tarnish to black. And that's just a thin surface veneer that forms when silver bonds with sulfur to create a silver sulfide compound, maybe like a little black powder. The sulfur here is coming from the atmosphere. So I guess one thing you should think about is that sulfur and silver, they want to react together. And so many of the economic ores, let's say you have silver and sulfur in the subsurface, well, they're going to bond to form different silver sulfides. So economic ores are also silver sulfides. Well, that's our main background. Now let's just talk about where it forms and some of the historical significance. So number 3 is going to be geologic occurrence. And just like gold, this is hydrothermal fluids. Hydrothermal fluids end up enriching in sulfur as it's scavenged. And in this case, the hydrothermal fluids must bear or be enriched with sulfur, must have sulfur-bearing minerals. And it is that sulfur that then will bond with the silver to form the ore minerals. And then the history of silver. Of course, we could tell so many different stories. I happen to be recording this on Columbus Day, and there's a long history of, I don't know, the positives and negatives of Columbus Day, right? And silver actually is a really important factor in that whole story, because here's a sunken treasure from the Caribbean where divers have pulled silver. Oh, look at that huge brick of silver, right? Silver from this shipwreck that was extracted from a mine in South America from the colonies of the Spanish Empire, and then was being brought back to Spain to basically run the Spanish war machine, right? And Spain dominates European wars using their Spanish Armada because of South American silver. So let's just say this. Let's say that the silver runs Spanish war machine for 250 years plus. It has a massive influence on the entire world, and European politics, because with the Spanish Armada, with all this money that's just pouring into Spain, they can afford to fight battles and dominate European politics. So let's just say that, like, this is associated with colonization of North and South America. We'll just say of Americas. This is associated with European politics. Anytime you're just flooding an economy with money, you destabilize currency. So that's happening at this time. Let's just put the word armada here. And of course, I don't want to make light of this, right? But we got to think, what is this colonization doing as well? Well, it is being associated with slavery. Bringing slaves in from Africa, but maybe even more significantly in South America, it's slavery of the indigenous people, and just how they're being terribly mistreated for hundreds of years, being forced to work in these mines, right? That's a big part of the story of silver. The deposits that the Spanish Empire uses are in Mexico and Peru and in Bolivia. And in Bolivia, that's not how you spell Bolivia. Bolivia. Okay, in Bolivia, there is a town called Potosi. And Potosi is home to a mountain called Cerro Rico. And Cerro Rico has like 60% of the world's silver deposits, or at least 60% of the world's production. Let me show you. Here's a picture of an engraving from hundreds of years ago showing this mountain with miners inside of it. Of course, it doesn't actually quite look like that. There is Potosi sitting under Cerro Rico, and there are hundreds and hundreds. Let's say, something I read it was something like 500 miles of tunnels just catacombing through this entire mountain as people have been extracting silver from it for hundreds of years. Well, maybe 500 miles might be too long as I just check my notes. It's hundreds of miles over 500 years worth of mining. Oops. The silver does run out. When silver runs out, this town was 200,000 people, a huge city in South America, and now the population is much lower, and it drops to around a population of maybe 10,000 once silver runs out. It's still being mined today, but for let's see if I get this right. Yep, it's zinc and tin is still very profitable to be extracted from here. What else do you want to say? Maybe I don't talk about it anymore, but if this thing fascinates you, go read about it more, because there's a huge environmental disaster going on here. You'd think all the catacombs of tunnels would cause deaths, and they do. There's every 5 to 10 years, there's a collapse because this mountain is so hollowed out. But also, all the mining has just polluted the soil and air and water in this region. And it's something that geologists now have to be concerned about, how to try to help fix that problem. Let's move on to the next mineral. Copper is our next mineral. There's our chemical formula is Cu. On the textbook, it is page 344. Our mineralogy of copper. Well, it's a metal, so a lot of things here aren't going to be all that different. Hardness 2.5 to 3. Specific gravity is 8.9. It does have metallic bonding and all the things associated with metallic bonding and closest packing, right? Ductile, malleable, conductive. That's what I want you to be thinking about. When it crystallizes, again, it should be isometric, but we don't see it that way. Put an X through it. And instead, most of the times, it is mined or discovered as these irregular masses that were deposited by hydrothermal fluids, right? You probably could have guessed that. So I guess we're kind of racing through this a little bit. Let's go, so here we go. Chemistry. It can either occur, thanks to its chemical state, as just native copper, native, right, and that's just Cu. That's what we're talking about today. But it also can occur as all sorts of copper sulfides. And you're going to learn a lot about these copper sulfides later in the semester because these are very important economic ores of copper. So we're just going to say we're going to save these for later. But chemistry allows it to occur in these two different ways. Our geologic occurrence is it from hydrothermal fluids mostly, but there can be other type of fluid percolation things that make especially the copper sulfides. But the one I want to teach you about the most, oh boy, I should show a picture, shouldn't I, guys? Let's show a picture of copper before I talk about the geologic occurrence. So when I talk about native copper, here's native copper. Here is a copper mine. Look at that huge mine where they're pulling out this greenish mineral. That's a copper sulfide. And so we're heading towards learning about these kind of minerals. And they'll be in these big mines, there'll be some native copper. But mostly it's these copper sulfides. But there are places in the world where there are just blocks, hundreds of tons each of just native copper that have been deposited from hydrothermal fluids associated with basalts. So let's say, and this is occurring in the United States primarily in a place called the UP. People from the north have probably heard of it. People from the south, maybe not. It's an area of Michigan. So we're going to say hydrothermal fluids associated with basalts will scavenge, let's say it this way, will scavenge and redeposit copper. Redeposit, let's try to spell that right, copper in vugs. Vugs are like openings, like a geode, or veins. And in the 1840s, this kind of copper was discovered in the United States. And it was discovered by people who found Native American diggings, and they had been mining this sort of stuff for hundreds of years. So in terms of history, we're just going to do a little bit. It's actually copper versus iron is like battling out to be the most important mineral and metal in today's society and economy. Iron wins because of steel, but copper is so important as well. So history in the U.S., we're going to say, should I draw this? If we do, okay, there, no, let's see, this is Lake Michigan. And then up here we've got, let's see, Lake Superior. And then there's this area. So then we have Illinois down here. This is an embarrassment to everyone. Here's Wisconsin. And then like there's this area up here called the Upper Peninsula of Michigan. Most Michigan's over on this side of Lake Michigan. But up in here, there are these huge deposits. Well, we're embarrassed of that drawing, but what we're saying is that in the Upper Peninsula of Michigan, there are massive deposits of just pure copper. Of pure copper. They were identified or discovered by Westerners in the 1840s, and they were mined pretty much extensively all the way through World War II. They're not active today. Let me throw in a couple pictures just showing the mining operations. Here's a picture of some underground miners, and this chunk right here, that's one whole chunk of copper. You can almost see the irregular mass nature of this. They would get smelted and then shipped off to the east. Here's a freighter that would go through the Great Lakes with all these ingots of pure copper. Well, last topic of today is going to be another metal. This is going to be iron. Oh, I put the chemical symbol first. That's okay. We can write it out as iron. Here in the textbook, this is page 345. And one of the most important things to say, this is like the mineralogy / chemistry. and that is iron is exceptionally rare on Earth. Very rare on Earth. That may surprise you, but we're talking about native iron, and the reason why, it's all because of oxygen. Right? You've seen rust before. Steel and iron can't exist in Earth because of our oxygen in the atmosphere causes things to rust. And so oxygen oxidizes. Right? That's a chemical reaction to make iron go to iron 2 plus or iron 3 plus. And so what we instead find on Earth is a mineral called, oh, let me make sure I do this right, where hematite, and that is Fe2O3. Oops, that's the 3 plus version. Or we'll find a mineral called magnetite, and that is Fe3O4, and that is 2 plus and 3 plus in its formula. So I might have made this somewhat confusing. Hematite is not the Fe2 plus. All right, let's just make sure that that's clear. But these are the iron-bearing minerals that occur on Earth, and we don't see pure iron. When iron is found, I guess we should do this. I go to 3. Where's 2? 2 is mineralogy. There is no iron mineralogy really to discuss. So you can make this be a 2 if you'd like to. So we have geologic occurrences. Where are we actually going to get iron in that rare instance when we can have it? Well, there's these 2 ways. One is in a banded iron formation. And let me show you a picture of some banded iron formations. This is what I want you to picture. We get these bands of the lighter material here. This is like shale, or it's chert. Basically, it's not iron bearing, it's just a sedimentary rock. But then it'll be interbedded with these layers that are red. And those layers that are red are probably mostly hematite. It at one time may have been pure iron, but it has oxidized. And there are vast domains in Australia and the United States and South America where the earth is just red like this. And what these are huge deposits of iron. And so we consider this to be like these banded iron formations. They hold about 60% of our reserves of iron that we can mine as ore. Very rarely there are banded iron formations where instead of this being red, it'll actually be pure iron. And that's from iron beds that were deposited in the Precambrian that have never been exposed to oxygen since. So that's kind of a neat rock that if you ever get to see it, put it in your rock collection. Our other geologic occurrence, oops, scroll down, of iron on Earth is actually extraterrestrial in origin. So our second is in meteorites. Sometimes meteorites will fall to Earth and they haven't had a chance to fully rust out and oxidize, and so there is an iron that can be found in them. We have iron, nickel. They're not pure iron, I guess is the point I'm making here, is that there are metallic meteorites that are composed of iron nickel alloys in metallic meteorites. These metallic meteorites are only represent 5.7% of all meteorites that fall, but because they look so strange, they don't look like a normal rock, they get oversampled. And so they're one of the more common types you can buy, even though they're not one of the more common types that fall. Let's put in a picture here. So here's what I'm talking about with iron nickel alloy meteorites. As they come into the Earth's atmosphere, they start to melt and they get pitted. But if you get underneath that rusted surface, you see this beautiful intergrown pattern of iron and nickel alloys. And the way this works, this is probably the only time this semester to talk about meteorites, but nickel and iron have same radius. And because they have same radius, they can make solid solution very easily. They make solid solution readily. there are these bands, and well, this is one of the things I want you to be able to take away from this. These interwoven bands of slightly different composition solid solutions of nickel and iron alloy, right? One's called plessite and one's called camosite. You don't need to memorize those. They're actually the names of the minerals. I want you to know that the interwoven bands of those two minerals make a pattern, and that interwoven band pattern is called a Widmanstätten pattern. We see that all the time in meteorites. So I want you to draw something like this. So here is our irregular meteorite with kind of like, it's got all these like cuspate bits. And we ground and polished an area right here. And in that area, we see a Widmanstätten pattern. So just kind of draw something like that to key into your notes what the Widmanstätten planet is. These iron nickel meteorites end up being the remainders of the cores of planetary bodies that are smashed apart. And it's one of our best ideas about what the core of our planet looks like. So let's say that these are remainders of cores of planetary bodies. And from the historical perspective, this is kind of a neat story about all these, is that for a long time, right, until the Iron Age, I guess, early peoples would mine the meteorites to use in tools. So in this happens to be King Tut's dagger. And this was the hardest, sharpest, most valuable weapon on the planet until iron was actually developed and people started making steel, because this is the hardest thing. It would just slice right through bronze. The Inuit people used meteorites that they would find across the ice fields, which would stand out as these black rocks on top of ice, and they would use them for spears and fish hooks and all these different things. So there's a lot of interesting history with meteorites as a historical valuable resource as well.